Good morning students. Hope you all are enjoying the online classes. Now let us start the second chapter. Here you will study about work, power and energy. Now let us start with the first topic, work. You have learned something about work in lower classes. Work is said to be done when force applied on a body causes some displacement on the body. That means work is said to be done under two conditions. There must be some force applied on the body, and on which body the force applied must displace, must have some movement in the direction of force. Okay, let us see one example. Here, first case, a body at rest and some force is applied in this direction, thereby the body displaces in the same direction of force. In this case, work is force into displacement. Simply you multiply force with the displacement, that will give the work. So the formula for work is force into displacement in the direction of force. Okay, then work is done in several cases. We can give the examples. When we lift a body upward, when we pull a body towards us, or when we move a load along an inclined plane, while climbing the staircase. These are some examples of work. Then work is a scalar quantity. It has no direction. So this is the conclusion. When force and displacement are in same direction, just by multiplying force with the displacement, you will get the work done. Now let us see another case where on a body at rest, force is applied in this direction, but the body displaces in another direction. A is the initial position, B is the final position. So body gets displacement in this direction, but the applied force is in another direction. There is an angle theta between force and displacement. In this case, we can't find out the work simply by multiplying force with the displacement, because displacement is not in the direction of force. Work is force into displacement in the direction of force. So in such case, how we will find out the work done? To learn how to find out the work done, you have to find out how much force is making this displacement. To learn, to understand it better, you must know how to break or split a vector. That process we call as vector resolution. This method tells how to split a vector, how to break or how to find out component of a vector. Look at this diagram. F is a vector acting at an angle theta with the horizontal. Okay, then how much force will act horizontally in this direction, we can find out. Look at this triangle. This force I have taken as the hypotenuse AC, and this is the horizontal AB, and theta is this angle, and this angle is right angle. So take the trigonometric ratio. Cos theta is equal to AB by AC. AC is equal to F. So you will get cos theta is equal to AB by F. So AB is equal to F cos theta. That means this side AB can be written as F cos theta. Similarly, this side you will get as F sin theta. Same application you can have here. If the force acts along this direction, means it makes an angle theta with the horizontal, then the component of force available along horizontal direction is F cos theta. That means the force, total force is F. Out of that, F cos theta is the force available along horizontal direction. Listen one example. Suppose a force of 100 Newton acts along this direction, and this angle between the horizontal and the force is 60 degree. Then how much force will be available in this direction, horizontal direction, that is F cos theta. F is 100, cos theta means cos 60, that means 100 into cos 60 is 1 by 2, so answer is 50 Newton. That means though the total force is 100 Newton, the force available horizontally is only 50 Newton. I hope you understood how to split a vector. Horizontal component is F cos theta and vertical component is F sin theta. This is the way to split the vectors. Now come back to the previous case. Here the force is F, displacement is S, angle between F and S is theta. So you can tell how much force causes displacement, or what is the force acting in this direction is F cos theta. F is the force, theta is the angle between the horizontal and the force between, angle between F and S is theta. So the component of force available in the direction of displacement is F cos theta, means the force which causes this displacement is not F, it is F cos theta. So in this case work is force into displacement, both must be in same direction. So the force here is F cos theta and displacement is S. So the formula for work is Fs cos theta. So this is the formula. When force and displacement are in same direction, formula for work is F into S. When force and displacement are not in same direction, if they make an angle theta, work done can be found out by this formula Fs cos theta. F stands for force, S for displacement, theta is the angle between F and S. Then this Fs cos theta can be also written as F dot S. It is also called the scalar product or dot product. Scalar product, or it is also called dot product. Actually you will study about scalar product, dot product, these things in higher classes. Roughly, just for your basic information, remember vectors can be multiplied in two ways, dot product and cross product. When two vectors are multiplied with cosine angle between them, that product is known as dot product or scalar product. Look at F is a vector, S is a vector, theta is the angle between them. So multiplying two vectors with the cosine of the angle between them, that is known as dot product or scalar product. Okay, and when two vectors are if the dot product is taken, the final quantity you are getting will be a scalar product. That means force and displacement. Force is a vector quantity, displacement is a vector quantity, but when you multiply these two vectors, the final result, work, it is a scalar one. Multiplying two vectors, but the result is a scalar quantity. That is known as scalar product of vectors. So better you remember, this is for higher classes. You remember this formula, work is equal to Fs cos theta. Now let us see different types of work. Work done can be maximum and minimum. Let us see when the minimum work is done. Minimum work means zero work. Work done is zero. Let us see when it can be. When the force can do zero work. See the first case, a man is giving a force on this body and the body doesn't move, means there is no displacement, S is zero, so F into S, that is zero, so zero work is done. That zero work is known as minimum work. Even though, for example, a man is pushing a wall, even though he pushes with all his might or force, the wall will not move. that man is applying force, but work done is 0 because there is no displacement happening. The force force, since the force can't bring a motion on the body, the work done is considered as 0. Then see another case, a man is carrying some luggage on his head and standing. Standing means he is stationary. So the gravitational force is acting in the downward direction. Against gravitational force, the man has to apply the force. So the man applies an exert force, upward force against gravitational force. So, and the displacement is 0. So the work done is 0. Force into displacement. That displacement is 0. So he does 0 work. No work is done. In both these cases, no work is done because displacement is 0. Look at third example. A man carrying some luggage on his head. So gravitational force acts in downward direction. Against gravitational force, the man exerts force. Okay, and he walks along a horizontal platform. Here the man was stationary, but in this case the man is moving. This is the direction of displacement. Let us calculate what is the work done here. Work done by the man or the gravitational force we will calculate. That is, we will use the formula Fs cos theta. This is actually general formula applicable in all cases, whether the body is moving in same direction of force or not. Generally, in all cases, this formula is applicable. If force and displacement are in same direction, this theta will be 0. Cos 0 is 1, then formula will become F into S. So the general formula applicable in all cases is Fs cos theta. Okay, so let us find out here. The work done is force into displacement, F into S, into theta. Theta here it is 90 degree. So F into S into cos 90. Cos 90 is 0. So work done is 0. Even though there is displacement, work done is 0. Consider the example of centripetal force. Last chapter you have studied. When a body makes circular motion, uniform circular motion, this is the direction of centripetal force and this is the direction of displacement. Angle between F and S is 90 degree, cos 90 is 0, so work done is 0. So these are the cases where 0 work or minimum work is done. Now let us see when the work done can be maximum or positive work. Look at this diagram. Force is applied on a body and body moves in the same direction. That means theta is 0. Angle between F and S is 0. So apply the general formula. Work is equal to Fs cos theta. That means cos theta value is cos 0. It is equal to 1. So formula becomes F into S. That means maximum work is done if force and displacement are in same direction. Or you can say when theta is 0, maximum work is done or positive work is done. In that case, the complete force causes displacement. Some more examples for maximum work or positive work. When a body falls downward towards earth, the gravitational force acts in this direction. In the same direction the displacement is, so maximum work is done. Another example, you are throwing a body vertically upward, so direction of the force and direction of displacement are same. In that case also maximum work is done. Now next case, work done can be negative also. Let us see when work done is considered as negative. Listen to this example. Here a wooden block is kept and you are applying some force in this direction and the body displaces in this direction. You know, when this body moves forward, this surface, suppose on a table surface it is moving, this table surface applies a frictional force in the opposite direction of motion. About frictional force in first chapter we discussed. So in this case, force is applied by you and body moves in the same direction. Let us find out what is the work done by the force you have applied. Work done by the applied force is F into Fs cos theta. Here theta value is 0 because F and S are in same direction. Cos 0 is 1. So F into S into 1, that is F into S. Positive work is done by your force. Now let us calculate what is the work done by this frictional force. Frictional force direction is opposite to the direction of motion. So frictional force and the displacement are in opposite direction. That means theta is 180 degree. Frictional force in this direction, motion in opposite direction. So work done by frictional force is Fs cos theta. Theta value is 180. Cos 180 is minus 1. So F into S into minus 1. That is minus F into S. Means a negative work is done. So work done is negative if angle between the force and displacement are at 180 degree. One more example. A heavy wooden block kept on the floor. Okay. And this is you, and you are applying a large force in this direction. Same time your younger brother exerts an opposite force, means younger brother applies the force in this direction. But the wooden block is moving in this direction. This is the direction of displacement. Since your younger brother exerts a small force, your force exceeds that force and thereby the wooden block moves in this direction. Let us calculate what is the work done by you and your brother. Work done by you is force into displacement. Both are in same direction. That means theta is 0. So work done by you is a positive work. You are doing positive work. Okay, what about your brother? Your brother applies force in this direction. Body movement is in opposite direction. So theta value is 180. That means work done by your brother is negative work. Okay, so work is negative if theta means the angle between F and S is 180. See some more examples. When a body moves opposite to gravitational force. Suppose you are throwing a body vertically upward. So you are applying the force in this direction. Displacement is in same direction. So your work is positive. But what about work done by gravitational force? Gravitational force and displacement are at 180 degree. So in this case, gravitational force is doing negative work and the thrower is doing positive work. Another example, suppose you are pulling a load by using a single fixed pulley. Your force will be in this direction, downward direction. Displacement of the load in upward direction. Angle between F and S is 180 degree. So negative work is done. Now work done can be found out from displacement time graph, Fs graph. In displacement time graph, displacement is marked on x-axis, force on y-axis. If a constant or steady force acts on a body, the graph line will be a straight line parallel to displacement axis. So here AB is the force displacement graph of a moving body. Then how can you find out the work done? Work done is equal to force into displacement. That means force into displacement means it is the area under the graph. This area, shaded area, that is area under the graph gives the work done. Then this area is in rectangular shape. Its length is represented as S, breadth is represented as F. So F into S is area under the graph. It will give the work done. Simply you make the find out the area under this graph, that will give the work done. Similarly, if a changing or variable force acts on a moving body, the shape of this force displacement graph will be like this. AB is the graph line here. And how we will find out area under the graph? Area under this graph is in the shape of a triangle. So here work done is area of this triangle. That means area under AB gives the work done. Then since it is triangular in shape, area under the graph. base, triangle in shape. So formula is half BH. Base means base is represented as S, and or you may use another symbol AC. So AC is the base, BC is the height. Okay, multiply it, it will give the work done. So the conclusion is, from force displacement graph you can find out the work done. Area under the force displacement graph gives the work done. Now units of work. It has CGS unit, that is dyne centimeter, and SI unit Newton meter. In CGS system, force is measured in dyne, displacement is measured in centimeter. So CGS unit of work is dyne centimeter. It has a short form, that is erg. SI unit, in SI system force is measured in Newton, displacement is measured in meter. So SI unit of work is Newton meter, its short form is Joule. Then let us see what is the definition of one erg and one Joule. Consider on a body you are applying a force of 1 Newton, thereby it displaces by 1 meter. Then the work done is known as 1 Newton meter, that is known as or defined as 1 Joule. So 1 Joule work is said to be done when a force of 1 Newton causes a displacement of 1 meter on a body. Similarly, you can make the definition of erg also. Consider a force of 1 dyne causes a displacement of 1 centimeter, then the work done is said to be 1 erg. Now let us see what is the relation between 1 Joule and 1 Joule and erg. How many ergs make 1 Joule? 1 Joule means 1 Newton into 1 meter. When 1 Newton force causes a displacement of 1 meter, work done is said to be 1 Joule. Let us convert each term into CGS system. 1 Newton is 10 to the power 5 dynes into 1 meter is 100 centimeter. So 10 to the power 7 dyne centimeter. Dyne centimeter, its short form is erg. So 1 Joule is equal to 10 to the power 7 erg. This is the relation between Joule and erg. Next term to discuss is power. Power is rate of doing work, means work done per second, that is known as power. So the formula for power is work upon time. So it is understood power depends on 2 factors, work done and the time taken. Power is a scalar quantity. Then power varies with the time. Let us see one example. Suppose A and B are doing equal work. The work done by A is 100 Joule, work done by B also same. Same work is done by A and B, but the time taken is different. Time taken by A, it is 5 seconds. For same work, B takes 10 seconds. More time B takes. Let us calculate the power of A and B. Power is work upon time. Work is 100 Joule, time is 5 seconds. Then 20 Joule per second. Joule per second is the unit of power. Work is measured in Joule, time is measured in second. That is the SI unit of power. It has a short form, that is watt. So SI unit of power is watt. Its expansion is Joule per second. And the definition of 1 watt you can give like this. When a work of 1 Joule is done in 1 second time, the power is said to be 1 watt. So here Joule per second can be written as watt. So the work done by A is 20 Joule per second or 20 watt. Now similarly, let us calculate the power of B. Work upon time, 100 Joule upon 10 seconds, that is 10 joule per second, that is 10 watt. So the conclusion is this: even though the work is same, since the time is different, power varies. So power depends on work as well as time taken. Less the time taken, more will be the power. Here more time is taken, so less is the power. More time is taken means power is less. About units of power, already SI unit at all, it is joule per second, having short form watt, and CGS unit is erg per second. This is the CGS unit and this is the SI unit. Then power is work upon time, and you know work is force into displacement. Work can be written as force into displacement upon T. This displacement upon T is known as velocity. So power can be also written as the product of force and velocity. There are two equations to calculate power. One is work upon time, the other one is force into velocity. Then this SI unit watt, it has multiples and sub-multiples. Bigger units of watt are kilowatt. 1 kilowatt is 1000 watt. Megawatt, 1 megawatt is 10 to the power 6 watt. And sub-multiples, smaller units are there like microwatt. 1 microwatt is 10 to the power minus 6 watt. 1 milliwatt means 10 to the power minus 3 watt. So this watt, it has multiples and sub-multiples. Then other than this, there is another unit called horsepower, HP. It stands for horsepower. 1 HP is equal to 746 watts, or approximately we take it as 750 watts. Usually the power of motor we express in HP unit. Now the conclusion. Let us find out some difference between power and the previous topic, work. Work is the dot product of force and displacement. Power is the product of force and velocity. In this case also it is scalar product or dot product, because these two are vectors. When you multiply, you will get power, which is a scalar. So it is also a scalar product or dot product. Another difference, work is independent of time, but power depends on time. Then its unit, work is measured in joule, power is measured in watt. These are some differences between work and power. Next topic is energy. Energy is the capacity to do work. If we have energy, we are able to do some work. For example, suppose we are lifting a body vertically upward. Okay, you are spending some energy in order to do the work. While lifting a body upward, the work done by you, or you will have some loss of energy, then the body will gain some energy. The body which does the work loses the energy. On which body work is done, that body is gaining energy. So work done and the energy are equal. That is known as work energy equivalence. Work done by a body is same as the energy spent by the body. Then about units of energy. Energy and work are same. So units of energy are same as the units of work. We have discussed about units of work. Joule is the SI unit, erg is the CGS unit. Then other than joule and erg, there are some more special units of energy like kilowatt hour. Usually electric energy, when we consume electric energy for commercial purpose, it is not measured in joule or erg, it is measured in kilowatt hour. 1 kilowatt hour we call as 1 unit. Electricity consumed at home is measured with a meter. In that meter, electricity is measured in this unit, kilowatt hour. Then let us see what is the relation between kilowatt hour and joule. 1 kilowatt hour means 1 kilowatt into 1 hour. 1 kilowatt means 1000 watt into 1 hour means 3600 seconds. Then 1000 watt, its expansion is joule per second into 3600 seconds. Second cancel. Answer is 36 lakh joule. That is also can be written as 3.6 mega joule. This mega stands for 10 to the power 6. So the relation between 1 kilowatt hour and joule is 1 kilowatt hour is equal to 3.6 mega joule. Then it has its small unit watt hour. Another unit of energy watt hour. 1 watt hour is equal to 1 watt into 1 hour. That means 1 joule per second into 3600 seconds. Second cancel. 3600 joule. So 1 watt hour is equal to 3600 joule. Then another unit, calorie. Calorie is an olden unit of energy. 1 calorie means it is equal to 4.2 joule, and it can be defined as amount of heat energy required to increase the temperature of 1 gram of water through 1 degree Celsius. That is known as 1 calorie. Then another unit is the kilocalorie. 1 kilocalorie is 4200 joule. Its definition is, it is the amount of heat energy required to increase the temperature of 1 kilogram of water through 1 degree Celsius. Then another unit, horsepower hour. Like kilowatt hour, horsepower hour is there, and it is not commonly used. Still, remember, there is a unit called horsepower hour. It is not common. Then another one is electron volt. Electron volt, this is the symbol. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. When we have to measure very small amount of energies, like energy of electron and all, we use this unit, electron volt. Then 1 electron volt is defined as the energy gained by an electron when it moves through a region of potential difference 1 volt.